Take a look at this. Do you see those devices? They're repairing the cell membranes.
What are they?
I believe you're looking at a form of nanotechnology. I've found thousands of these in both aliens. They're not just regenerating the damaged tissue, they're repairing the mechanical components as well. As far as I can tell, this arm's as good as new.
This scene, depicted from a popular TV show, Star Trek Enterprise, represents how most people view nanotechnology. Tiny robots flowing throughout your body, repairing, healing, and possibly even improving. Is this what nanotechnology is? Is this the direction scientific research is going? We dive further into the details of nanoparticles and their possibilities to find out. According to the National Cancer Institute, 1,665,540 new cases were reported in 2014 alone, with a 5-year survival rate of 66.1% and total estimated deaths of 585,720. The total 2014 budget for the National Cancer Institute was approximately $5.1 billion. Recent developments in cancer treatment include radiation therapy that uses high doses of radiation to damage the DNA within cancer cells and shrink tumors. And we have all heard of the traditional chemotherapy treatments. However, a major issue regarding chemotherapy is that while it may kill the cancer cells, it also kills surrounding, healthy, functional cells. To avoid having toxic drugs coming into contact with healthy cells, nanoparticles can be used to not only protect non-cancerous areas, but also deliver higher doses directly to the cells we want to kill. They are so small that they have the ability to enter a cancer cell, to deliver localized drugs, and provide a novel cancer therapy technique. This novel technology shows us just how amazing working at such small scales can be. The nanoscale field works with particles that are 50,000 times smaller than a human hair. Nanoparticles are any piece of matter that is between 1 and 100 nanometers, or 1/1,000,000th of a meter, that act as one unit. Their small size leads to a large surface area that allows for diverse functionality of the surface of the nanoparticle to localize to desired molecules for biomedical applications. They can be made from polymers, metals, and biological agents. One such polymer nanoparticle consists of a small liquid droplet of a certain chemotherapy drug, such as inactive cisplatin, that is encapsulated by a polymer shell using monomer polymerization or polymer dispersion techniques. Encapsulating cells into nanoparticles is a method that is used to attenuate the effects of immunorejection as a result of foreign objects being placed in the body. The cells then secrete therapeutic proteins and remain in the system without being rejected. Synthesis consists of the polymer self-assembling around the droplet in the presence of surfactants, resulting in a hydrophobic core and hydrophilic shell. To increase stability within the body, polyethylene glycol, or PEG, is added to decrease oxidization and prevent the foreign nanoparticles from being rejected and flushed from the body. This is then coated with the necessary bioactive markers such as cell internalization agents and targeting ligand or protein, allowing the attachment and uptake into the cancer cell.
I don't know about you, I was kind of worried. Instead of regurgitating all the knowledge that we know, why don't we take a physical look and see how these nanoparticles are actually made, how they enter the body and destroy cancer cells. I will lead you through this journey. Don't worry. I'm a scientist. First thing we have to do is make our nanoparticles. So let's go ahead and do that.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
Science rules.
Bill Nye the Science Guy.
Inertia is a property of matter.
Bill Nye the Science Guy.
T minus 7 seconds.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy.
Science.
Okay, we got our nanoparticles. I'm gonna show you that in slower motion. The solutions and equipment are 20 mLs of gold hydrogen tetrachloride solution, 2 mL of sodium citrate solution, 1 ml of sodium chloride solution, distilled water, magnetic stir, and hot plate combination. Now let's make some nanoparticles. We'll start by adding 20 mL of bulk solution to the conical flask. We'll heat the solution until it boils, which usually takes 4 to 5 minutes. We'll keep it stirring to ensure even heating. The watch glass on top of the conical flask is to prevent the solution from evaporating. Once it boils, we'll remove the watch glass and add the citrate solution. You can see the color change. It's gone from light gold through a blue color phase. As we continue stirring, you can see the color change again to bright red. The red color indicates we have produced nano-sized gold particles around 10 to 20 nanometers. This is the chemical equation for the redox reaction, where gold ions react with citrate ions to form gold atoms. As well as acting as a reducing agent, citrate ions act as a shielding agent wrapping around the cluster of atoms. This creates an electrostatic sheath around each nanoparticle, which prevents agglomeration and stabilizes the particles. Let's look at the prepared nanogold solution. Pour distilled water into one tube, gold chloride into a second tube. So our solutions are distilled water on the left, gold solution in the center, and the nanoparticle solution on the right. We now shine a red laser beam through each of the test tubes to find which, if any, have particles. Gold nanoparticles are colloid, so we can't see them, but we can usually detect them by the refraction of light. You can see the entry and exit points, that's all. There's no visible passage of light. If we shine it through the gold chloride solution, we get the same result. The suspended nanoparticles are reflecting and scattering the light as it passes through the solution. You can see the passage of light as a red beam from one side to the other, a response known as the Tyndall effect. We have indeed produced gold nanoparticles. We will now increase the size of the nanoparticles and observe how that impacts the color and size. We will add to one of the test tubes a few drops of sodium chloride solution and shake it well. We observe darkening of the color. By adding sodium chloride solution to the original gold nanoparticles, we have caused the particles to increase in size, which affects the way they reflect light and therefore changes the observed color. Adding sodium chloride disturbs the electrode sheath around each gold nanoparticle, resulting in positive attraction, agglomeration, and therefore size change. Okay, now that we got our nanoparticles, let's take a look and see what we got. Ooh, pretty. Wait, you can't see this. Hold on. Alright, now we can see into the strange world of our bodies. Funny how the inside of our bodies looks a lot like a whiteboard. And look, we found a cancer cell. Let's look what happens when we introduce our secret agent cancer-killing nanoparticle. Look, they're in love. Aww. What will happen next is the cancer cell will envelop the nanoparticle and thereby its doom.
She call me Mr. Bombastic, tell me fantastic, touch me on me box, she says I'm Mr. Rowe.
Now the nanoparticle has made it past the cell membrane, it can begin to degrade, releasing its deadly poison. Poor guy, he doesn't look so good. One major feature of cancer cells is that they inhibit apoptosis, which is the process of programmed cell death. Chemotherapy drugs like cisplatin introduce apoptosis of the targeted cell, ultimately resulting in cell breakdown into vesicles, which are then removed by phagocytes. Now the cancer cell has been destroyed. Hooray! And the peasants rejoice.
An additional type of nanoparticle used for cancer drug delivery is gold nanoparticles. They are synthesized by reduction of gold salt in the presence of surface stabilizers and exhibit attractive physical, chemical, and optical properties. As with the PLGA nanoparticles, the surface is coated with PEG to increase biological stability and uptake. Additionally, the surface is coated with linker molecules that attach to the gold surface on one end and contain an amine or carboxylic acid functional group on the other. This functionalization allows the cancer drug to be cross-coupled to the nanoparticle. Gold nanoparticles also have the ability to be functionalized with active ligands at densities 100-fold higher than conventional liposomes and 1,000-fold higher than the PLGA nanoparticles previously discussed. One application currently being studied is the surface functionalization of gold nanoparticles with DNA that contains cellular prion protein aptamers. The aptamer ligands on the nanoparticle identify to the cellular prion protein expressed on the neuroblastoma cells, providing the aptamer-coated nanoparticles with high specificity in addition to low toxicity, high affinity, and ease of synthesis. Some of the cancer drug is released when the aptamer on the nanoparticle is recognized by the cellular prion protein on the cancer cell, increasing drug concentration in cancerous tissue surrounding the cell. Further uptake occurs through endocytosis, where the DNA that contains the cellular prion protein aptamers are degraded by nucleases and release the rest of the therapeutic drug, inducing cellular apoptosis of the cancer cell. Whether made from magnetic iron oxide, gold, or polymer, nanoparticles have been shown to have novel applications and astonishing experimental results. What else could we use these amazing nanoparticles for? Maybe soon we will come full circle and actually produce the tiny body-repairing robots from Star Trek. But for now, using pieces of matter 1/1000th the size of a meter to locate and kill cancer cells within our body is pretty incredible.